Hi, everyone. My name is Charles. I'm really excited to actually kick this off today with the Smart Laboratory of the Future section. So I'm not going to belabor this point because there was a fantastic first presentation, but the 28 billion number, what I want to put in context, though, is that pharma R&D expenditure in the US is about $50 billion, right, a year. So I think that these numbers together really show how much of an impact we can have in solving or at least making a dent in some of the reproducibility issues. So I'm the CEO and founder of BioBright, and at BioBright we're actually building the smart laboratory tools for the future, in particular in pharma. So keep that in mind when I talk. I'm going to talk through that lens as well. Oh, there we go. And I want to share a few paradigms that we've actually deployed and that we've learned from doing these smart laboratory deployments in pharma. The first one is what I call don't automate, augment. And I realize this may be a bit controversial, but the point is that we've had automation for at least a decade, good automation in pharmaceutical research and in biomedical research in general. What we haven't done really is create a system that is more symbiotic between humans and machines, one that augments human scientific capability. Here we go. And the point that I'm trying to make here is that we should optimize for the relative strengths and weaknesses of each one of these systems. So automation is really good at throughput and reproducibility and repeatability, but there's no quality gauge. A robot doesn't know whether what they're doing is correct or not. There's always a scientist guiding that experiment at the end of the day. And on the other hand, humans are really good at intuition and interpretation, but our working memory is relatively small, or maybe I'm only speaking for myself. And so the point that I want to make here is that there's a level of human-computer interaction that we really need to drive to the next level. We can't achieve another 10x or 100x improvement in reproducibility if we don't tackle the problem of human-computer interfaces. And many people in this room are actually tackling this problem. We had conversations even just this morning about this. But the point is that human-computer interfaces are actually changing very rapidly. I don't know how many of you may have an Alexa or a Siri at home, but what used to be computer UI, user interface, graphical, is now morphing into a much more multi-dimensional user experience. And so there is voice now that comes into play. For the last 2 years, we've actually been working on a voice assistant that we call Darwin, which is very similar to Alexa or Siri, but the major difference is that it's really tuned for augmenting the scientist in the lab. And so whereas Siri may really be tuned to ordering pizza, ours is really tuned for ordering reagents. And we should have audio on this, by the way. Let me just go back for a sec here. But the point is that Darwin is a keyword here. And so, well, I'll just speak it out. But Darwin, go to blotting preparation is what's being spoken right now. And then it's Darwin, take a note that I order some more nitrocellulose transfer packs. What I want you to pay attention to is really the vocabulary here, right? Siri would never get nitrocellulose transfer packs because it's not really a common consumer word, maybe our kind of consumer. And so again, transblot turbocassette. So the point is that we've really targeted these custom vocabulary that are very complex to transcribe accurately otherwise. And you can imagine going forward that you can even do much more than just take notes. You can drive robots with this. And the robot can then automate the tedious and complex parts of driving it such that it just returns a fully baked request with the protocol already baked in. All you have to do is load it into the computer. The second paradigm that I want to share is really this notion of data-driven discovery. And now I know that we've collected more and more data in this field, and I think that we're suffering the pains of it. But one of the things that we still have to change is our mentality around biomedical research. This is a kind of meant to be tongue-in-cheek, but this is what pretty much biomedical research looks like today. We generate data, we collect it in lab notebooks. Some of those are electronic these days, but then eventually it makes it into a PowerPoint. We share that information with peers. It makes it into a bigger PowerPoint, into a bigger PowerPoint, bigger PowerPoint, and eventually, if you're lucky and efficient, every 6 months, there's a decision level that will actually occur, and you'll decide to steer the company in one direction or another, towards one indication or towards another indication. What I would like to share is really kind of a different mindset where the scientist and every person at the company has the ability to ask questions directly. You can get files back, but more importantly, you can also get most active contributors. And this is because biomedical research is fundamentally a mix between quantitative and qualitative data. So don't treat this just like computer science, where everything is pretty much quantitative. It may be better to actually just talk to the best contributor because they have all the intuition of the system. And you can go one step further. This is a demo that we did in augmented reality, where you can actually just have the data pop up in context right in front of your eyes using an augmented reality display. And we went even one step further, thanks to a contract with DARPA in particular in neuroscience, where we actually integrated multiple electrode signals, multiple data streams into a single visualization. And the point that you should remember here, this is too complex to go into detail, but is that when data visualization is done correctly, data visualization can become data analysis. This is extremely important when we have a large amount of data to whittle down to and to try to reason about as humans. You can imagine, obviously, coffee breaks where you can just walk past the data and now spur conversations. The point here is that the machines are doing the tedious work that machines are good at, and humans are focusing their entire time on actually building intuition and trying to make decisions of their experiments. This is not just beautiful and pretty and awesome. We actually did improve the precision of a particular workflow, a complex neuroscience workflow, by more than 20 times, and we cut the number of people required in half. The point here is that there are really tangible metrics that you can control with. And this picture is complex, but what I want to say here is that we all play a role in bringing this data-centric model to life. Everybody, from pharmaceutical companies down to bioequipment manufacturers. And I'll leave you with this quote, which is that I think that if you are removing the tedious aspects and the burdens from the daily workflow, and you turn that into an opportunity for discovery, I think this is what we should be trying to strive for, something where we are much more symbiotic with machines. So thank you. I'll take any questions.
Is this commercially available, Darwin, or is it still is it still a prototype?
No, it is commercially available. We're working with a restricted number of partners, but yeah, it's available. Yeah.
Can you describe a couple of the successes you've had in the implementation?
Sure. So I described some of the early work with DARPA, and we're now working with pharmaceutical companies. I can't give you hard numbers, but roughly, there was, for example, a high throughput workflow where we found about 30 times more errors than they were before. We think, and the operative word is think here, that this has really led them to choose the wrong molecules for development. So obviously, this has a big impact in pharmaceutical workflows. Mm-hmm.
Quick question, is there in the future going to be a version for academics, or pharmacy is the only focus? I know why you're starting with it makes perfect sense, but academics obviously can benefit just as much.
Yeah, so we have collaborations, in particular with the Sanger Institute. They're going to become public imminently. We do have partnerships with some academic centers. The tricky part is how to really, is the money, is where it starts with. So that's why we're starting pharma. My ideal scenario would be that this would be available almost for free for academics. We're trying to figure out how to do that. Yeah. Awesome. Thank you.
Hi, everyone. Might maybe bring this down a little bit. So I'm Bethan from Bento Bio, and today I'm not going to be talking about automation. I'm going to be talking about people. And at Bento Bio, what we want to do is to make learning biotechnology hands-on as easy and as simple as possible. So.
You have the clicker there.
Oh, brilliant. Do I?
Yeah.
You do now.
I do now, okay. So today we're talking about the future of the laboratory. And what I'd like to talk about is who will be in that laboratory of the future. So this little guy, in 10, 20 years, what does the laboratory that he's going to be using look like? And where will that be? So to start off with, I'd like to share an analogy. And so on your left, you've got computers 50 years ago. They were huge, they're expensive, and to use them, you often needed a qualification. And on the right, you've got laboratories of today. And you can see where I'm going with this, especially because we've made the photo black and white, but we have some of the same restrictions within a laboratory now. And now we've progressed to this point where you can buy a computer like an Arduino or a Raspberry Pi for $30. And what that's meant is that it's also changed the types of people who are using computers. So you have maker communities that are using these Raspberry Pis and Arduinos. And the shift of users is really where I want to draw your focus and attention. Because, for example, your 8-year-old could program themselves a smartwatch. So at Bento Bio, we're building a portable DNA analysis laboratory. It contains all the kind of standard bits of kit molecular biologists use on a day-to-day basis to do DNA analysis. But for us, the focus here was to actually change the design so that it focused on friendliness, on user accessibility. And it was actually something that you could literally carry around in a bag with you. So last year we actually launched this on Kickstarter, and that was really interesting for us as well because it was a public platform, so it's changed the type of people that we've attracted. And some of the user stories that come out of that are really interesting. So as you might expect, we've got traditional scientists, but rather than doing the work in the lab, they're doing it on top of a New York skyscraper or in a Madagascar jungle. We have people that are doing pop-up science education, and that goes from New Zealand to a rural community in Haiti. And then, more interestingly, we have citizen scientists. People who are doing science outside of an academic institution without support. So this is Gianpaolo, and he's doing a project where he looks at the genetic ancestry of yeast. So ideally, you could say to him, I really like this Red Church IPA. And he'll say to you, cool, this other Tiny Rebel IPA is genetically similar, so maybe they'll taste the same, and you should give this one a go. But Gianpaolo fits into a much larger movement of people that are doing this. It's a global community. So there are people all around the world that are teaching themselves to do biology outside of a lab, from scratch. They're computer coders, artists. And this is a picture of a meetup that I attended, actually taken by David Kong in the room, where people were sharing techniques and projects and what they were doing. And last month, David actually hosted a global meetup in Boston at the MIT lab. And there were people coming from Burma, from Chile, talking about bioprinters, using liquid handling robots. So it's a much larger movement, and it has all these different kinds of names that you might have come across: biohacking, DIY bio, citizen science. So just going back to this guy, today we're talking about exponentials. Exponentials in terms of how to make the technology faster, cheaper, more reproducible. At Bento, what we want to focus on is the people. How do you enable bottoms-up innovation? The future of this technology is not just going to be in how it develops, but also in the number of people that are using it. And with a technology as powerful as biotech, we also have a responsibility to create better educational resources and ensure that we're innovating responsibly. So you might recognize this guy. This is George Church, and he is a supporter of the DIY bio movement. And last month, he actually described Bento as an Apple II moment. So it's kind of nice to have reassurance that it's not just us that believes in this future, but also him. And And just in terms of finishing, my ask for you today is if you had access to a lab outside of your own work and you wanted to explore a question, and maybe you wanted to do that with your son or your daughter, what type of question would that be? What would you use your laboratory for? And how might that look in the next 5-10 years? Cool, thank you. Yes.
Do you have an age group that your bento box is basically directed towards?
I mean, I guess ideally, if you look at the school curriculums, it's sort of 14 plus, but we've worked with kind of like 10-year-olds upwards. It depends what the ability of the child is, I guess.
Thank you. This is a really cool concept. My question was, do you have tie-ups with communities in developing countries? And you did mention it, especially the school children, for doing their own science experiments?
So what was the first part of that? Do we have
tie-ups with communities in developing countries or schools in developing countries?
We're starting that. It's so we have links to communities in, well, like I mentioned, Haiti and India as well. And then I think how that develops is how well we build relationships and partnerships, and how much resources we have.
Hey, over here. Hey. Have you thought about working with curriculum publishers to, bundle your Bento Bio with it?
So can you give me some examples?
So McGraw-Hill or like some of the big kind of biology curriculum publishers. Just a thought.
That's actually something that's come out of. We might be. It's very recent, but a suggestion from someone. Yes. And then there was a question over here.
What would you say to someone who might think democratizing genetic engineering is terrifying?
That's a question that we get asked a lot. And I think that, so the rough answer is the more education that people have, the easier it is to recognize something that's terrifying and something that's not. And this type of equipment is already available via eBay. If you want to get your hands on it, you can. So the question is about, people are rejecting things like GM technology because they're scared of it. And the argument doesn't always line up, but I think that part of that fear comes from a lack of experience and a lack of getting hands-on. What we're pushing for is to say, well, let people experience this and learn about it, and then they can make up their mind. But more education has got to be a good thing. Same with sex education, right?
How much does this cost right now?
So it's £1,000, which I'm not sure what the currency rate is at the moment, but that's like $1,300, $1,400. It's going down all the time in terms of US dollars,
And
unfortunately.
Just one follow-up. What is the issue with providing reagents?
So that's been a really interesting work for us, is to look at freeze-dried materials or alternatives to using restriction enzymes. There's some really great, it depends what kind of reagents you're thinking about, but you can find polymerase that will last at 37 degrees for a month, or enzymes that last up to 3 months at room temperature.
But do you work with vendors for simple liquid reagents, for plastics, for pipettes, those sorts of things?
Yeah.
That come in?
Yes.
To provide special packages and scales?
Exactly.
Okay.
Cool. I think I'm being cut off, so I'm going to, thanks very much.
Hi, my name is Rachel. I'm from Science Exchange, and it's an outsourced marketing or marketplace platform for outsourced R&D, if you guys have not heard of Science Exchange before. One of the biggest things that we're really trying to do is to enable scientists, whether from pharma scientists, industry scientists, biotech, to academic researchers, to really be able to outsource their projects efficiently and have access to world-class labs that are able to do their projects as well. So some of the biggest challenges that we've really seen in outsourced R&D is that there's just really a lack of knowledge in who's the good lab to use out there, and which supplier, if you Google it, how do you know that they're actually good, or they're just, really advertised based on the keyword search. Another thing that we've also seen is that once you do find a lab, do you know if you're able to work with them right away? Do you need to set up a direct contract with them? If you work in an academic facility, who do you work with, to make sure that you can actually do the MTAs and MSAs and things like that? Directly contracting can take up to, months, if not a year, to actually set up your project properly to move forward. So what we are, we're a platform, an online platform, with over 2,500 service providers, CROs, academic cores, that are all pre-contracted with Science Exchange. And so if you're a researcher and you sign up and you have a contract with us, then you're able to work with these service providers quickly and efficiently. Another thing that we also do is we handle a lot of the billing and kind of the tedious administrative work that you may have when you're trying to work with outsourcing platforms, and simplify that process for you as well. And one of the other things that we also have is a concierge team. So it's a team of PhD, masters, and industry-trained scientists that are available free of charge to use to help you find an appropriate lab to outsource your research. We also help with project management support. So, you're working in a lab, you don't want to check whether or not your outsourced project those milestones are being met. And so we can help handle that for you as well. One of the other things that Science Exchange has been involved in, and our concierge team has been involved in, is really sourcing and managing the reproducibility project for cancer biology. Some of you have probably heard about this before, but it's one of the largest public biomedical replication projects that are being undertaken. And so not only are we involved in the cancer biology project, but our co-founder, Dr. Elizabeth Irons, has been really on the forefront of managing and starting a lot of reproducibility projects via Science Exchange as well. So these are just a few that we've been involved in, including private validations for pharma companies. So one of the major ones that we've been doing is a reproducibility project for cancer biology, which is a collaboration between Science Exchange, the Center for Open Science, as well as eLife, to really produce a large replication study taken from 50 high-impact cancer biology papers, and conduct them by third-party independent labs in our network to ensure that the key figures are, showing whether or not they're actually reproducible. And so what we have so far is we've been able to complete 11 of these replication studies, and 7 of them are already published and available to view on eLife. And at the end of this project, which will be coming up near the end of this year, and so we will be doing a meta-analysis of all of the completed replication studies to really see kind of which steps in trying to do a replication study and how the process is undertaken. What factors can maybe contribute to a study more likely being able to reproduce. And so this is just a snapshot of the types of projects that we have in the reproducibility project. You can see that they have a wide variety of techniques that are being tested, as well as a wide variety of cancer types, in this project. And this is just a snapshot of some of the labs that have been involved in the reproducibility project that are also available on Science Exchange. They range from CROs as well as academic cores in the US. And so I saw that I only have about 2 minutes left to speak, so I'm just going to quickly run through just a snapshot of how this is being done for a couple of the projects. But essentially what we have is we have the original article that we have picked out from 2011, 2012. And then during the time of the project, we wrote a register report to really ensure that the protocols were peer-reviewed before actually starting any experimental work. Once the experimental work was conducted, we wrote up the replication study, and that was also published and peer-reviewed and published in eLife as well. And this is just an example of one where there was the replication study that was done was to test the effect of cimetidine on human cell lung carcinomas as well as renal cell carcinomas. And they found that the effect of cimetidine was able to actually decrease or have a effect on the tumor growth. And the replication study was able to show the same effect as well. I'm just going to skip through this one. But I really wanted to highlight here is that a lot of the previous reports about running replication studies showed that it was very inefficient and really difficult to get started and very expensive. And so what we found is that from our published studies so far, that the average time to do these was about 6 to 7 months, which included in vivo studies. And the average cost was anywhere between $16,000 to about $15,000 or $50,000, which is a really low cost compared to what some of the studies have shown to do these projects in-house. And so I just wanted to actually, I saw the time that we needed to get to questions and answers. So I'll end on this. This is our platform that you'll be able to access through scienceexchange.com. And we do have a place where you can easily place your concierge requests, easily search for labs. And then this dashboard is also a way for you to easily kind of track and manage all of your outsourced projects.
How do you QC the contractors that you work with?
Yeah, so that's a really good question. So we are ISO 9001 certified, and we have SOPs that actually require a desk audit by our regulatory affairs team to ensure that they meet either the GLP or GMP or any certifications that they say that they have. And they also have a really strict application process. And so our team of providers, kind of a service provider management team, checks them and runs them against any FDA complaints or any other complaints in a proprietary software as well.
So I'm a science provider, and one thing that comes up a lot from clients is why don't I just call you? How do you guys deal with the... So you guys, I think you charge about 10% off the top or something like that, or at least I think that's what my clients pay. And a lot of them come to me and says, well, can I just call you? And, and you know, I say no. But how do you deal with stuff like that?
Yeah, no, that's a really good question. So the circumvention kind of, aspect of it. So we actually offer a few advantages if you keep everything on platform to our service providers as well as to our requesters. So one of the things is similar to Airbnb, where they encourage you to keep everything on platform because if something goes wrong, Airbnb cannot indemnify you. We also have an indemnification clause as well. So if something goes wrong, Science Exchange is there to really help arbitrate any disputes and things like that. And we also handle the payment process. So there is a guarantee of payment as long as the work was completed as described in the SOW to the service providers. And we don't charge the requester until after the work has been completed and satisfactory as well.
So maybe just a question on the scientific reproducibility, because this is obviously something that could help in terms of, that you would be required or more likely to be accepted in a journal if you had like an anonymized third-party lab that verified your results. So are you aware of any such movements? Are you guys thinking of progressing in that direction?
Yeah, so this is actually where we found a lot of pharma companies like using us to do these kind of one-off projects to determine whether or not they should even move forward in a particular study. And so that's actually where we've partnered with a lot of pharma companies who are now using Science Exchange for their outsourced research. And they find that really doing it for these reproducibility studies are very valuable, especially since you're able to do that by a third party, as claimed,
I don't want to presume, but I think I know the answer. The question is, for your reproducibility initiative, the publications, so you have the protocol published, right? And then the full study. So when you review or send it for review in a peer-reviewed journal, eLife, are the reviewers blinded? Are you blinded to the reviewers, or you choose the reviewers, or?
For the reviewers, we do not choose the reviewers. I would have to check actually to see, the blinding of that. Yeah, but I can check that and get back to you on that as well.
Thanks.
So one last question. Early on for the cancer reproducibility project.
Early on, for the Cancer Reproducibility Project, Elizabeth Irons alluded to the fact that it was actually a lot more expensive than originally planned, which to many of us was not necessarily surprising. But now the numbers that you're showing actually indicate that it's surprisingly cost-effective and efficient. So what's changed?
Yeah, so I think in terms of the ones that we've had published so far, it probably is because those ones we were able to get the information from the original authors a lot quicker. And so again, these were only the statistics from the completed studies so far. It would be good to see the meta-analysis of all of the studies to get a better estimate at that average cost.
Okay, quick question?
Keep moving. Can you catch her at a break? Thank you. Okay, our next speaker is Douglas Densmore, who could not be with us this morning. So he's helicoptering in remotely. And we want to thank him because he spent a lot of time working on the steering committee for this meeting and helped to really improve it.
Okay, I apologize that I can't be there. I can hear my voice a lot. Sorry. I apologize I can't be there. This is probably the worst way to give a talk, and I'm really excited about this meeting. I do want to thank the organizers. If there are questions, feel free to, there's any numbers of ways you can get a hold of me, so please do shoot me an email. I'd love to talk more with folks. I wish I could be there. The other thing I realized is this is probably the worst PowerPoint to walk someone through because there's lots of animations, but I think we'll make it through. So are we seeing the title slide then?
Yes.
Okay, good. So if you go to the next slide and you animate through about three things, you're going to see what I do. So in my group, just to give some people some context, what I have is I have a research group called the Cross-Disciplinary Integration of Design Automation Research. We make software for synthetic biology. Once that software has matured, it's then turned over to a nonprofit called the Nona Research Foundation, which maintains open source synthetic biology software. Then companies like Lattice and Asimov, two companies which I'm involved in, can then take that software and do commercial things with it, as could any other company. So if we animate through this slide a couple times, again, eventually what you'll do is you'll see a list of logos. You'll see things Cello, Merlin, Eugene. These are all software tools that my group makes. The reason I bring them up in this meeting is because all of these software tools rely on automation. All of these software tools, at the end of the day, are trying to do something either in a more replicable way, scaling up biology, connecting biology with computation, et cetera. So all of these things, all these software artifacts are going to require an automated environment to actually produce what I call wetware. Most of what I talk about in my talks is that we have software. The software ends up using hardware like microfluidics or electronics and ultimately produces wetware. So to do that, we need automation. So if we go to the next slide should have the Cello logo at the top with the Biological Design Center and MIT. I just want to give you one example of a software that would need automation. If you step through about 3 animations, again, maybe 4, you get the fact that this is making a genetic compiler. So one of the things my group tries to do is take high-level descriptions of a function. We want to turn function into DNA. So again, software making wetware. And if we go to the next slide, which is slide 4, and again, the animation through this is not important. If the person controlling just were to step through this, what you'll see sliding through the frame is the fact that high-level descriptions of functionality are turned into circuits, and then those circuits ultimately get mapped to DNA library elements. And kind of the last piece in that animation at the bottom, if that's showing, is that those large sets of circuits, when we make an individual circuit, we end up making lots of variants. So again, back to the theme of this is that the software making wetware, we don't just make one circuit, we potentially make thousands of circuits, depending on the space of designs that's available. And not only is that going to be hard to manage intellectually without computing or automation, but it's also going to be impossible to manage the data flow. It's going to be impossible to capture the rules and learnings. So all of this will be required an automated environment. So the next slide, the things, again, that happen if we can step through all of this slide. What's happening in this slide is basically the fact that high-level tools like Cello make design plans and then ultimately at the end go to the twist tool called Puppeteer. So I hope you're seeing that. I know there's lots of animations. But the idea being that what I'd like to talk about in this meeting for people to think about in the lab of the future is how we can connect high-level computational designs to their physical realization. And there's people like myself and other people that are thinking about how to do that now, and that's what I'm going to talk about for the rest of my talk. So slide 6 that has the picture of nature, I don't think I need to talk to this group. We can go to the next slide. We know automated labs are going. So then on slide 7, we're talking about another article, and I just want to point this out. This is the gist of this article is that we're not going to have robotic butlers, so the robot of the future doesn't look like the robot from Rocky IV or something where we actually have people moving, a robot like humans moving things around. It's going to be taking kind of existing style automation and connecting that in intelligent ways, both from a software standpoint as well as their physical realization. So slide 8, I heard the beginning. We can go to both of these. I know we've already talked about the picture on the left. Reproducible research is key, but then also there's going to be a complexity that's important to handle. Nothing, I think, is new. So on slide 9, this might be new to folks. I think Wei-Min Zhao is speaking later today. He may touch on this. Something that I had talked to him about, he started this idea, is the fact that there could be a global biofoundry consortium. So the idea would be people like the BioFab, iBioFab at UIUC, and places like the DAMP Lab, which I'm going to talk about at BU, might be placed in the United States, along with researchers in Edinburgh, Manchester, and Tianjin, where we might make a consortium of academically based biofoundries. And the idea would be to set up shared knowledge, to set up sharing standards, repositories, round tripping. Basically, not only it'd be important to have an academic set of folks thinking about these issues, but not only thinking about them, having the actual laboratory infrastructure to test these out and to work with industry that does have this often. And so if we go to the next slide, slide 10, this could be a biofabrication leader in that thought space. So the idea is if I want something physical, if we animate through this one at a time, AdGene is what we think about for plasmids. We have iGEM, we think about electronic registries. We think of the BioNet that Drew Endy and others at Stanford lead, thinking about a way to do materials tracking and transfer. And so the Global Biofoundry Consortium could be the standardized manufacturing side of that. So we've got physical, electronic, tracking, and then we have a manufacturing side. So that's something that I'm sure Wayman will be happy to talk about in the breaks. I'm happy to talk to folks outside of this meeting about this Biofoundry Consortium and how we could keep moving with that. Next slide, slide 11. You can step through that. So one of the things we're doing at BU is making the damp lab. I made a joke that it's not wet, it's not dry, that's why it's damp. It stands for design, automation, manufacturing, and prototyping. And so what we do in that space is we both do the manufacturing of wetware as well as the manufacturing of low-cost, continuous flow microfluidic devices that are used for synthetic biology. The next slide, 12, just shows that I noticed when I was looking through the International Gene Synthesis Consortium that places like the Edinburgh Genome Foundry were on here. So there was this fact that we had commercial partners, but also academics. The DAMP Lab, I hope sometime in 2018, will also be a member of this consortium. So if we go to slide 13, where is this located and what's going on at BU? This is a picture of myself, Chris Chen, Mo Khalil, and Wilson Wong. We've started a new center for, and again, I'd love folks to visit. We have other members of this now. Allison Scrow, Mary Dunlop, for example, John No, are also part of the Biological Design Center at BU. We go to the next slide, slide 14. You can step through some nice pictures of this. There's about 3 or 4 animations that show different pictures. This is a new building built right on the main strip of Boston, right down Commonwealth Avenue. Slide 15.
We're going to need to head into Q&A in a minute.
Yep. Okay, so we can go right now. If we just skip to slide 19. Apologies, it's very hard to see the audience and it's hard to do with the animation. I'll just leave this with this last point. So what I want this community to know is that this BioFoundry integrated instrumentation system is coming online at BU. I would love to have a dialogue with folks about how we could connect other software, other hardware, and other infrastructure into this system and make it available to the community.
Great, thank you very much. Actually, that went pretty smoothly, Doug.
Good morning, my name is Branden Brough, and I'm going to give you a little preview on how the Department of Energy, of all places, aims to democratize science, especially in the biomedical arena. So I am the Deputy Director of the Molecular Foundry, which is this lovely building overlooking the bay up here. So take a BART ride, come visit us. So we are one of 5 nanoscience centers. And nanoscience is defined very broadly for its, so it's basically anything small, so therefore it's anything biomedical. We are one of 5. The other 4 are in other national laboratories in New Mexico, Tennessee, outside Chicago, and outside New York. And we are knowledge-based user facilities. And so I think looking at the other talks that have come before me, we talked about the need to share expertise, the need to share software, hardware, all these types of things. We are a knowledge-based user facility, meaning that we invite scientists from around the world to come to Berkeley, come use our facilities, and come interact and collaborate with our scientists. Because we are a multidisciplinary research center where our staff, who are world-renowned researchers in their particular fields, spend half their time doing research and half their time lending their expertise to the scientific challenges that users from around the world need their expertise for. So this is, again, the Foundry from the other side. There are 7 different facilities that we provide free access to. The first 3 listed on the right side are in the business of synthesis, so making materials. We are focus primarily in a materials space, but that doesn't exclude really any types of basic science. The one that is probably most interesting to this audience is that 5th floor, the biological nanostructures facility, and I'll talk a little bit about what they do. But when you are trying to make new materials, especially small materials, you need to also have your engineers and physicists that are in the business of understanding, creating computational models to understand how they behave, fabrication folks who are doing some of that top-down fabrication to make lab-on-a-chip types of systems, microfluidic systems, and of course next-generation characterization so that you know what you're making. The other benefit of coming to a place like the Molecular Foundry, on top of being free, is that you get to access all the other different facilities at the national labs. A lot of people don't realize that there are 17 national labs that are funded by the Department of Energy, and many of them are creating things that go boom, but a lot of the other ones are in basic science and just basic science. And so you have the Molecular Foundry, which is listed there. A lot of people go to the Advanced Light Source, which is one of the world's best sources for soft X-ray. A lot of X-ray crystallography is going on there. The JGI, which was part of the Human Genome Project. So people come, they use the Molecular Foundry, they make or they look at whatever they're doing, and they can also access some of these other great facilities. So very quickly, kind of how do people gain access? There are 2 calls per year. They're very short proposals. For those of you who have sent proposals into the NIH, you'll be very happy to know that not only do our proposals only span 2 to 3 pages, but also the success rate is in the 70% range, right? A lot better than the 20 pages and 10% range for the NIH. This gives you free access for 1 year, and you can use that year however you like. You can come in for 1 day, use a really powerful microscope or a robot or whatever, and leave. You can come and make this your home institution for a full year. As I said, free for non-proprietary research. So this basically means basic science. We have a lot of industrial partners that come in and operate in a pre-competitive model, and so they get free access as well. And it's all done through external peer review. So what makes a good proposal? It's basically, that top one. It's scientific impact. There's a lot of other things that we measure as far as, how will the Foundry be able to benefit this research, kind of a fit question, but really it's what's the most interesting scientific model? And so we talk about democratization of science. It's basically wherever the best idea comes from, we want to make sure that they have the access to the people and the equipment necessary to explore those ideas. So here's a snapshot of kind of who uses us. You can see that's a large number of institutions across the country, across the world. 11% from industry. I think it's up to 12% now. And some pretty impressive folks, National Academies members, Nobel laureates come and use it. But we also have, early stage professors from teaching colleges or small startups as well. Wow, that's a busy slide. This is something that's a favorite of our directors, just kind of the shock and awe approach of our science, but really I'd point you to the top left corner, gives you a sense of how big we are. So we're about a $30 million annual budget that supports something about 45 research staff that are full-time here. And supporting, we're coming up on 1,000 users a year or so. This is a real quick snapshot of some of the biosciences that we do. We have combinatorial synthesis for mostly peptides and peptoids. Ron Zuckerman might be a name you're familiar with. He is not only the inventor of the peptide synthesizer, but also the peptoid, the artificial self-assembling biomolecule. We do a lot of work with biological assemblies that interface with non-biological systems. A lot of bioimaging development. Nanoscience, of course, is quite advantageous in in creating new bioprobes, and of course, cryo-EM, cryotomography is something that we're very strong in. And so that's it, trying to keep you on time. Thanks so much.
Are people able to do sort of fee-for-service work? Are they able to rent space, or is it all through grants? Are small companies able to?
They are. A lot of the small businesses would prefer to go the free model, of course. Regardless if you're going to pay for it or not, you still need to be above the bar scientifically. So basically, if you think about this, if you have a professor that is writing for a proposal for grant money from the NIH, they get money and they do some science. The benefit to the taxpayer, the benefit to the country is the knowledge they produce. And so really the purpose of this place is to facilitate great science and produce great science. So it's not so much an incubator space if there isn't a strong scientific question that is being answered. Does that answer your question?
Yeah.
Yeah.
I'll try to be polite, but
go ahead.
How has the political climate treated you in the last year? Does Rick Perry know you exist and are in Berkeley?
Rick Perry does know that we exist. Basic science, ironically, has always done well, regardless of political party. And if you actually chart it, Republicans tend to appreciate basic science more than Democrats. If you look at a chart, I think that the big challenge with DOE and politics is in the applied side. So with basic, we're actually doing fine, and if the Senate bill goes through, we would actually end up with a 12% increase. So someone over in DC likes us.